All right. Question. Hey, Huay. I can see the top of your head, but I can see your feet. No, I don't see anything. If I don't hear any question, I'm going to go back to the debate. Cindy, Hoya, Hoy. Can you give the form about the post-lab? The formula? Which formula? You mean the how do you solve problems with the projectile motion? Is that a question? I can hear if you're saying something. I don't understand. We just want a formula. It's a formula of free fall in y and constant velocity in x. Aren't there any questions? I mean, pretend you're coming to see me in my office because you have a specific question or you don't know something. Let me show you one thing. You can let me share my window. No, I can't share my window because I don't have anything to share. So if you place the cursor on your screen and bring it down to the bottom of your screen, you have a green folder with an arrow on it saying share screen. You can click on it and then you can show things or some window or some problem you were working on it, and then I can help. I can see what you're doing. You can take a picture of some development you have and upload this picture on your computer, and then you can use that share screen to show me your development, and then I can say something, and then I can write correct. I can write on your development. I can do things. You know what I mean? For instance, let me give you an example. I'm going to share one screen I have here, which is this screen. It's an NFS, right? So it's a, I was reading this thing. So you could, if you have a stylus, you could annotate, you could write on it. Let me see. You can write on it. You can do things, and then we can communicate that way. It's very efficient, um, right? But if you want your formula, so when you do projectile motion, you divide in two components, one for x and another for y. So this y component is a free fall, right? So basically x is equal vxt, and this is constant. And in y, you have these two basic equations, y minus y naught, v naught y, t minus half 9.8 t squared. The other one govern velocity, change it, v naught y minus gt, and the other one is Bernoulli, vy squared, v naught y squared minus 2 times 9.8 times y minus y naught. So, but I mean, formulas are not the issue. The issue is to have the ability of understanding the problem and and kind of navigate through these different things. And by the way, so tomorrow exam, as I mentioned to all of you, is based on chapter 2 only. Okay. All right. So I don't know what to do. You guys are muting there. I don't know what you guys are doing. Oh, Tree here. Hello. What will you provide on the cheat sheet? Equations. Is projectile motion? No, it's not. Projectile motion is chapter 3. Chapter 3. I might have a copy of the formula here. Let me see. File open. Vinha, some alarm going on. I'm trying to find the formula sheet. I think equation sheet. Midterm quiz. So the quiz. Quiz 2 equation sheet. Where is it? I thought I had it. Equation sheet. Oh, there you go. Now let me show you this. Where is the chat room? There you go. Here is. Oh no, you cut my showing. I was going to show my equation sheet. Okay, just a second. Here is the equation sheet right there. That's the one. You see that? So then you have average definition of average velocity right there. This is motion with constant velocity right here. This is the equation for velocity with a constant acceleration. This is position with constant acceleration, Bernoulli, and projectile motion, right? So basically that's it. This is what I'm going to give you guys tomorrow. Okay. There you go. All right. So somebody was showing me something. What was it? Oh, wait a second. There was lots of discussion going on. How many problems? Oh, I don't remember. But it's enough to get you guys done in 1 hour and 15 minutes. On one of the questions you put on the practice quiz. Okay. Cindy, a soccer ball is released from rest at the top of a grassy incline. Okay, after 6 points. The ball travels. On a second later, the ball reached the bottom of the incline. And what the ball assumed. Okay. Okay, no problem. So what's your question on it? You said you had a question. Why don't you show the problem and put in the screen? Can you share the problem? Was there some sort of a class sheet? I can try to find what it is. I mean, oh, it was on Moodle. Oh, no, I don't know what it is. Okay, so let me answer your question about the initial velocity. So about So I'm assuming the initial velocity is 51 meters. Now, initial velocity is the velocity the ball has when it is released. So look at this. Let me see if I can annotate on top of this. I don't think I can annotate. Let me see if I can find a problem and then I can solve it for you. Just a second. You said was in Moodle, right? In fact, let me copy this over. Copy. Let's go to page. New. Okay. Now share the screen, and I'm sharing this one. Okay. So here's the problem. Annotate. Can you see my screen? Can you all see that? So you have a soccer ball released from rest. You know what this means? This is your initial velocity. So the ball is released from rest. So the ball is not moving, but it's in an incline. So you do an incline like this. And then you hold the ball up there. You hold, and then you let it go. So when you let it go, the ball starts moving, which means the initial velocity of this ball is 0 meters per second. If you take what you did, 51 meters, you divide by 6.3, you are kind of determining average velocity, right? Ignoring acceleration, by the way, because you have acceleration there. You are taking final position, 51 meters, initial position 0, divided by time, you have average velocity. That's not initial velocity, okay? So after 60.3 seconds, so in a time that is 6.3 seconds, the ball traveled 51 meters. So the distance the ball traveled, del x, this is final position, right? Minus initial, which was the beginning position. So that is 51 meters. So this is pretty much the given information. 1 second later, the ball reached the bottom of the incline. So, which means the ball is falling down, right? And then get to this point here, 6.1, so 6.3 seconds later. And then 1 second later, so this is 1 second, it reached the bottom of the incline right there. So the ball goes 6.3 seconds up to here, and then it moves another 1 second. Okay. So situation A, question A. What was the ball acceleration? So how do we find the ball acceleration? So we go to our equation of motion in which acceleration is included, and that is x minus x naught is equal v naught t minus half times acceleration times t squared. So x minus x naught we have is 51. Initial velocity is 0 minus, plus the acceleration is in that direction and the velocity too, so they are both positive, plus half acceleration times 6.3 squared. So your acceleration is equal after you do your math, is 2 times 51 divided by 6.3 squared. And this is in meters per square second. And then you calculate that. Okay. So Cindy, is that okay? Don't you have a microphone, Cindy? You can talk to. You can click on a microphone and then you can communicate. Because I don't know what you're doing there. Can I hear you? Yeah, better.
Yeah, it makes sense now.
Okay. Now for part B, how long was the incline? So you want to find this whole thing here. How long, right?
Yeah.
You want to find this whole thing. So this whole thing is you could figure there are different ways of doing. One is, you know, the ball, the travel time for the ball is 6.3 seconds plus 1 second. So the total, see if I can move this. No, I can't. So the total travel time to the bottom of the incline is equal 7.3 seconds. So this total time is equal 6.3 seconds plus 1.0 second, so 7.3. So we want to find how long was the incline. We want to find distance, right? We want to find, if you will, xf minus x naught. That's the size of the incline. And then you use the same equation, basically exactly the same equation, except that now you know the value of acceleration and the time is calculated, 7.3. So the whole length of the incline is going to be equal to initial velocity, which was 0, times the time, 7.3, plus half of this acceleration here. So you calculate this number, plug it in there, times 7.3 squared, right? And then you can figure your the length of that incline. Good enough?
Yeah, that's good. Thank you.
Okay. You go back to stop share. Can I stop sharing? I mean, I'm taping this, right? You can review later. So let me go back to the chat and see if there are other questions. So no, don't assume that's not correct. It was a mood. Da-da-da. Do you curve the exams? No, I don't. I don't apply centripetal acceleration to the exams. No, I curve class participation, the clicker thing, labs. I doesn't matter because it's not a lot of on the weight towards your exam. But no, exams is the whole deal. If you can do your exams, you're good. So I use exams as a way to ensure the student know what's going on. Okay. Yeah. Oh yeah. Yeah. Oh, yeah. The lab is the fun part. You have a lab on Newton's law. Tomorrow we will be using a motion sensor in the beginning, but then we will be using um, a a different sensor or detector called photogate. And the photogate is a sensor that keep timing events with very good precision, and by doing so, you can translate that timing into velocity. And I will show better tomorrow. Well, I feel I try not to say similar problems. I could say a similar problem like the one you show me is a car is going down the hill um, with the initial velocity of 10 meters per second, and after um, 30 seconds, it has displaced, um, let's say, 700 meters. And then I can ask, what is the velocity of the car at that moment? Something like that, you know. So it's the same problem you just showed me, but I'm not talking about soccer ball. I'm not talking about an incline. I'm talking about a road. So it's the same problem. The steps you use to solve the problems are the same. So if you really understood how to solve this problem, you could solve any other problem that has the same steps. So in that sense, yes, it's pretty much similar. Yeah. Usually I do a range of four, 0 to 4, 0, nothing was done. One, you initiated and you had a good start, but it was not. You started, but you got lost in the middle, right? You really didn't start. No, I do half points if the problem was most of it done, but it had in fact, two very crucial mistakes, like mistakes with sign that are important and relevant. This is a bad one. Or you have a error in orientation, which is also important. So if you have each error now, I mean, you did the problem, you got a solution. It's not the right one, but you made a mistake that was physically wrong. Then I take points. So if out of four, you can go two, three, or four. Four is completely right. Even if you make minor errors because your calculator had degrees instead of radians or radians instead of degrees, something silly that it's doesn't affect the physics of how you solve the problem, I give full score. But if you make a crucial error, I take points. So two crucial errors, I take half. And three is usually I don't have three crucial errors. I don't give that chance. The problems are either direct or is a two steps type of problem. I don't give three steps, not for physics way. Homework on forces? No, I haven't started forces yet. I have to push that forward. I will do that. Have to go to WebAssign and do that. We do that right now. So that is chapter 4, right? Schedule. Okay. How about October? No. Which day is today? 26, 27, 28, 29, 30. Okay, up to Saturday. No, it's not Saturday. No, I this is chapter 4, right? Chapter 4. There you go. That is going to be due on October 5th. Okay. Okay, done. Any other question? I try not to answer this question about. I mean, exams will be based on class sheets, type of problems, homework, but don't memorize situations. Try to understand how you solve problems. That is the main point. So every Monday I will open this chat room, and today was a good start. But to make it work nicely, would be great if you come with questions. So now you know you can have in your computer a sheet with questions, right? And then you can show them to me, and then I can go through them with you. So we could use that Monday morning to kind of get in shape um, with the content we are doing class. And I don't know if your notes kind of giving enough time for you to mature the information. And tomorrow is our first exam on chapter 2, although we are now in chapter 4. So I'm expecting now you are a little bit more seasoned in physics than you were before. So things will start developing from now on. So next time, next Monday, bring questions and be a little bit more active so we can use this hour to do good work. I mean, this was a good work, but we can do better. All right. Do you have any other question? Can you please help with homework problems based on cars? Number 6. You have to be more specific. What is the problem with homework problem? This is the type of thing that I try not to do is to solve the problem without you attempting. So I know chapter 2 homework. I know, I understand. So the best thing to do, I mean, I will solve for you, no problem. But next Monday, when you say, okay, can you solve a problem such as such? What I want you to do is to show me what you have done so that I can see what was the problem. Because if I just solve, you don't learn. Trust me. All these problems, they have solution online. You can Google, you're gonna find somebody post the solutions online without the need of pay. So, but how do you learn? You learn when you get yourself facing different situations in physics, right? Different problems, and then you try to solve, and then you get stuck in something, and then you look for help. Then you email me, and then you show me what you've done, and then I can go ahead and help you. But if you just ask me to solve, you're not gonna learn, and I assure you that. Okay, let's stop this speech and see what you need. So which problem? Choose one. 6, 7, or 8. Which one? Raman, 6, 7, or 8? Problem 6. Okay, so let's find that one. Let me go to WebAssign. This you said was homework? And this is chapter 2, I think you said. Chapter 2, problem 6. This is chapter 6. Hello? I was, but I'm in online now. Okay, problem 6. I got there. I don't understand. Oh, it's funny. When I open the problem, I get the solution done. Okay, a car is driving at a speed of 97 kilometers per hour. Okay, let me share this with you now. Let me go here, share the screen. Yeah, we all did. Where is it? Where is it? Where is it? I think it's this one. Yeah. Can you see? Is that the problem you're looking for? Now I can't see the chat room. Roman, can you unplug your microphone so I can hear you? I don't want to talk to the walls. I need a little feedback. Do you have a microphone? Yeah, there you go. Very good.
Yes.
Okay, so is that the problem you were looking for?
Yes.
Okay.
That's the problem I'm looking for.
Okay, so then you have a car. Let me annotate that. Okay, so you have a car that is driving with the speed of 97 kilometers per hour. So let's write the given information. And so speed 97 kilometers per hour. And I have a meter somewhere there, so I'm pretty sure we have to convert that to meters per second. So 97, and now we are converting to meters per second. Okay. And just as the light changed from green to yellow, so you're driving the car, the light is green, and then it changed to yellow. So what you gotta do? Well, depending on where you are, so if you are way far, you have to stop pressing the brake, right? And then the car stopped. Or what you should not do is to speed up and try to pass the intersection, which might cause an accident. But let's keep reading. If the driver has a reaction time of 0.92 seconds, so this reaction time, this driver is a pawhead or is drunk. 0.92 seconds is a lot. The human reaction time we can measure in the lab is about 0.2 seconds. 0.92 seconds, is drunk. It's a drunk driver. Okay, if the driver has a reaction time, so reaction time 0.92 seconds, and the braking acceleration of the car, so he sees the light, right? And then when he sees the light, he doesn't do anything. I mean, he thinks about pressing the brake, but the reaction time is the time that it takes his intention to be transformed in action. So first he sees the light changing, and then he presses the brake. So there is a time that he'll still be traveling and moving with 97 kilometers per hour. Kilometers per second? No, kilometers per hour.
per hour.
Yeah. Oh my God. Per second is a very fast car. So I have to convert that hours. So 1 hour, I have to convert that to 3,600 seconds. Okay. So basically, essentially, the velocity is going to be, or the speed will be 97000 divided by 3600 meters per second. So he will still keep this same speed for 0.92 seconds. And then the brakes will kick in and the car will decelerate, if we can use this expression. Find the minimum distance, x minimum, the car travels after the light changes before coming to a stop. So let's do a little sketch of what's going on. So here's the point the car stops. Okay. Now, this is the point the car travels with a constant velocity given by this number, 97 kilometers per hour. And then, so this velocity is constant. Now here, in this situation, up to full stop, the car has an acceleration that is also constant. See? So the difference is, in the first segment, the acceleration is 0, right? There is no acceleration here. An acceleration that is implies in stop. So, and you want to find the minimal distance that the car moves. So you want to find this distance over here, x. So your x is equal to, if you call this x naught, plus this x over here, x final. Right? Are we all good? So what is x naught? I'm going to copy the numbers from here. So this is pretty much 26.9 meters per second. So x naught is the distance the car covers with constant velocity, and that is 26.9 times the time, which is given by the reaction time, 0.92 meters, right? So take this speed, multiply by the time, you have the distance, which is given in meters. Now, how do you find x final? So x final, if you take this whole del x, right here, this whole distance del x, so x final is equal to v naught t, right? V naught t, because at this point the car has an initial velocity. It was moving with 26.9 meters per second. Oh, wait a second, I don't know how long it took the car to stop. I have the acceleration, but I don't have the time. But I want to find the distance. I could use Bernoulli. Let me use erase. Bernoulli is that equation that allows you to measure things. Where is my marker? Color, undo, erase, spotlight. I don't want that draw. It's funny, where is my marker? Wait a second. There you go, annotate. Okay. So Bernoulli equation is final velocity is equal initial velocity square minus 2 times acceleration times the distance the car travels that time. So when you don't have the time given, you can use this equation in square because the time is not part of it. See? Now, your final velocity when it stops is 0. So this is 0. And then you have to solve this. V naught squared is equal to 2 times 5 times the distance xf we want to find. So xf, therefore xf, is equal V naught squared, which is 26.9 squared, divided by 10. 2 times 5 is 10. And then you have your xf. You plug it in here, and then you can add. Okay, you add the two segments, and then you have your solution. Good enough? Who asked that? Was
Yeah. Thank you.
Okay. All right. Very good.
Thank you so much.
All right. Wonderful. Any other? Nope. Okay. So see you mañana. Oh, let me see if I have any.
Are you gonna ask these kinds of questions, or more like a homework problems or something?
This problem, it has a second 2 levels development. Sometimes I do, sometimes I don't. But yeah, so you should be able to fish a couple of informations there. One is you have a segment that has no acceleration, and you have another segment that has acceleration. There are complex type of problems when you have two different situations. Like I think I put in the homework one of the train. There you have a two trains. They are moving the same track. One has acceleration, the other doesn't have it. So what make the two situations common? What parameter is the same for both of them? Is the time when a train collides. I don't know if you guys have seen this problem before or if you try to do it in a book. So this problem is a little bit more complex. I didn't do in class, and I put in homework because I expect you guys to work on it. But again, you need to ask me questions. Don't just go to the classroom and forget about me. You have to really get involved and ask questions. Okay. I know some of you are doing service learning. You have the opportunity, and you are forced to go to the place and stay with 4C students. But you have my office hours, and you know where to find me. Okie doke. All right. Let's see. Oh, wait, towards an intersection, does the light change from? Yeah. Can you go over the graph problem on chapter 2 homework? The one asked about acceleration, please. Can you go over the graph problem on chapter? Let me see. Share this. I think I have to go first and find the problem. Chapter 2. The chapter 2 homework, I don't see any graphic problem. Who is asking this? Can you please unmute your microphone? Is it problem 9? 3, don't you have a microphone? Okay, I'm assuming it's 9. So you have a graphic. You have a graphic velocity versus time. Oh, wait a second. What is it? You have a graphic velocity. Oops, sorry. You have a graphic velocity versus time. So as we saw in the lab, the slope of velocity versus time gives you acceleration, right? The slope of a graphic velocity versus time gives you acceleration. So in the following graphic, it depicts the motion of a car. Find the instantaneous acceleration at time 2 seconds, 4, so on, so on, so on. So time 2 seconds is right here. So the instantaneous acceleration is the slope at that point. But you have a line here. So the acceleration, the instantaneous acceleration is going to be the same here, the same here, the same everywhere. It doesn't change. And is equal to what? And is equal to definition of acceleration is equal to final velocity minus initial velocity over time interval. This is the definition of average acceleration at that point. So it's the slope, because this is a straight line. So what is the final velocity? This is the one at this point, 0. What is the initial velocity? The one at this point. Now what that one is -3 divided by the time interval. The time is in second, so it's 1 second up to here is point, it's 0.6 perhaps. The time is not exactly in the middle, it's 0.6, so it's about, it's not 2 seconds, it's not 1 second, it's not 1.5, probably 1.6, I guess. So the average acceleration is 3 divided by 1.6 meters per square second. And then you have a number. That's how you do that. I'm not getting this number 2, but this might be wrong. Unless the significant figure is short. So, okay. So this is my 2 meters per square second. Now for 4.5 seconds, 4.5 seconds, what is the instantaneous acceleration at this point? Well, you do the same thing. Final velocity looks like 3 minus initial velocity 0 divided by the time interval looks like 1 second. Then you have your 3 meters per square second. Now at 6 is right here. Final is 3, initial is 3, so 3 minus 3 is 0, that's why you got a 0. And time 8 seconds, this one, final velocity is -2 minus initial velocity -3, so you have -5 divided by the time interval 1 second, 2 seconds, 3 seconds. And this is meters per square second. Okay, good enough? Good enough? All right, very good. No, which hour? No, service learning has to be done with the students with 4C. I can't have that. It's not gonna work. So the only students that are my understanding are doing service learning are um, those students in the table. And today I couldn't even mark them, but they were there. And you have to do with the 4C students so that they will give you some recognition for the 4C student. In my class, I mean, those points that I said I was going to give can only be given to the students who are working with the 4C students, right? Because it's a way I have to reinforce participation of them in the tutoring program. Okay? All right, you all. So see you mañana. Hope this becomes more active next time. All right, but it was good. Love to see you guys there. And I will upload this in the computer.